right. Am I here? Where am I? Woohoo! Good morning, everybody. Can you hear me? Yes, I should be there. Can you hear me and see me? Testing, testing. One, one, two, three, five, eight. That's the Fibonacci sequence. You guys know that, right? One, one, two, three, eight. Yes. All right. Good morning, everyone. Okay, I'm going to pre-apologize. I have a wonderful and immense headache today, so I may not be the most eloquent person, but I've taken some medicine, so hopefully it will wear off very soon. It's very, very, very hot here in Cambridge today, so I don't think I can do this without the air conditioning today. So apologies for the background noise too, because it's just right here. The machine is just right here. um, how is everybody doing? Welcome. And I see a lot of familiar faces as usual. Makes me very happy. Monique, Arasto, Albert, BVR. I don't know what that stands for. Hari Prasad, how you doing? Rodolfo Torres, Andrés Obregón. How are you guys doing? Cheers to Parametric Camp's ninth anniversary. That was, I have to say though, technically it's the 15th of July, and I forget why. I need to check with my brother, but I know that we agreed to make it the 15th of July be the anniversary, but I forget exactly why. I think it was the first day of the first workshop that we taught, or something like that. I'm not. I have to look at but the idea is that Parametric Camp. I think I've told you at some point in the videos before. Parametric Camp is this initiative that my brother Fernando and I started 9 years ago today, and it was because back in the time, imagine 9 years ago, Grasshopper was barely a thing, and we were all like learning, and it was like very, very, very much in the infancy of a lot of this. So there was a lot of people who wanted to learn these techniques. So my brother and I started this international workshop. So it used to be a 1 week intensive, like 5 days, like learning in the morning and exercise in the afternoon, and then a final project on the second week. And we used to travel. We traveled Europe, teaching a lot of these workshops. We traveled Spain. We taught a lot of these workshops, and we did that for 3 years. And then we stopped due to a combination of personal and professional circumstances. And so when I started this initiative now, the YouTube live stream, etc., I just thought that taking the name back and like making it now same spirit. It's all about teaching and sharing the wonders of computational design. But now, 9 years after, like, you could argue that Grasshopper is a bit more popular, it's a bit more widespread. The way we learn things is different, so I wanted to give it more of like a modern outlook to the same idea, right? And that's why, now it's more of like a YouTube channel with a Discord community, and maybe at some point when things get a little better, like we can go back to organizing events where we actually meet in person and we spend some time working together and learning about things. So that would be really cool, actually. But anyhow, that was 9 years ago, and it's today, and I want to keep celebrating every year. 10th anniversary. What are we gonna do for the 10th anniversary? Huh? I think that one we should actually meet in real life and do like a hackathon or something. That would be really cool. Do I have photos of 10 years ago? Do I have them? I think I have them for sure, but they're not accessible easily. I may have them on some hard drive. So maybe I can show them next time or something. Also, I had so much more hair and so much darker. and, and and my beard was like fully dark, you know. And yeah, good old times. Anyway, so, but back to today. What are we doing today? Today we're doing several things. We're doing overview is going to be I'm going to shoot a couple of parts of previous videos that I forgot to do. So if you remember from last stream, we made this small gem that was calculating calculating a point between 2 points, you know, or like a point along a line. I would like to, and we did that with normalized coordinates, so relative to where the point was. I would like to do like a small addition to that video where I implement the same concept, but instead of just normalized coordinates, so relative coordinates between the 2 points, I would like to do it with an actual Euclidean distance, which is just changing the algorithm a little bit. So I just want to add that. I need to record the introduction to that video, which I forgot because you guys didn't remind me. Now, like you usually remind me, but we all forgot last time. So I need to record that introduction so that we can publish the video as a gem. And I'm so excited. This is so cool. Remember last week we were going to implement Chaikin's algorithm for creating a smooth curve between a set of control points, but we couldn't. And then we came up with the idea of making it a challenge. And I'm so happy about the challenge because so many of you have actually given it a try and you've done it in vanilla Grasshopper with the Grasshopper plugins. You've done it in C#. You've done like different iterations, different models. I'm actually so excited. So I want to talk a little bit about that, and then I want to propose my own implementation. And actually, what I find interesting is that out of the questions that I've seen from the people who tried the challenge, that has inspired me on how I would like to implement. Because, like, for example, there were some questions about trying to close the control curve, and people could not really figure that out. So I think I want to give that a try and see if we can extend the algorithm to make it like a closed polyline, etc. And how would that work? So I think that should be really interesting, and I want to give that a try. But before, I would like to remind everyone that you can subscribe to this channel if you like what you see here. I mean, probably most of you already, if you're in the chat, you're probably subscribed to the channel. But just a reminder for people who may watch this video in the future. And a reminder that we also have a Discord channel. We also have a Discord channel. We have offline conversations in between streams, and that's where, for example, we had all the conversation about the challenges, etc. I'm enjoying that conversation a lot. So if you want to join the Discord, please go to this link here, and then make sure to go to the introductions and introduce yourself and say who you are, where you're coming from, etc., so that I get to know you a little better. We all get to know each other a little better, and we build a little bit of community, right? That's really nice. Woohoo! And then after all of that, as usual, we'll do like 15-20 minutes of Q&A and social. All right? How does that sound? Is that a plan? Hmm? Can you give me a thumbs up, thumbs down, thumbs so? Okay. So, all right. So, where are we starting? We are starting with some Rhino, and yeah, we're finishing the gem that we did like 2 weeks ago, 3 weeks ago. I forget. I don't know. It's summer here, so as you know already, I've taken a couple of weekends off, you know, because I also like going out in the nature and hiking and going to the beach and doing those human things, you know. Sorry. And yes, and I see some questions, Leandro. Maybe we can leave those kind of questions for later for the Q&A. All right. So if you can remind me of that question, we can talk about that later. All right. Thank you. And all right. So where were we? I want to pull up files from that gem because I probably want to continue doing that. And where are we? I am recording this, right? Yes. 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 Mm-mm. Oh, and something that I want to do too is for those of you who submitted the challenges on the Discord, I want to reach out to you personally and I want to ask you for your permission to repost your example as part of the repository that we have with examples and the gems, whatever, so that other people can access the file that you have done and and that might be an inspiration for them. So if you posted an example for the Chaikin's algorithm challenge on the Discord, I will probably text you or message you or whatever and ask you for your permission to publish your file in the parametric camp repository where the files for the Chaikin algorithm gem will probably be. So I think that's something that I want to do also because it's part of how I feel we can build community together. And if you have done an example, some work on some code that other people could benefit from, I think it's nice for you, it's nice for them, it's nice for everybody that we all share that together. And maybe the parametric camp repository is a good platform for doing that. So it's up to you. I see. I'll talk about that later when we get there. So where were we? We were on here, point along the line, and I made this thing. So this was the file that I finished the other day, and we had 2 points, and I'm going to, yeah, and oopsie. So what I did, sorry, again, I have quite of a headache today. Yeah, this is not what is going on here. All right, let me bake this point. Let me bake this other point. And now let me set the 1 point up. No. All right. I don't know what I'm doing, so I'm just going to create these 2 points from scratch, and I'm going to clear this value, and now this is going to be. I just want to move the points around to so that I can show like, hey, this works, etc. You know. And and the point being, the other day what we did was like, we found a point along the line, but we found it in relative coordinates. So if the point is at 0.5, then that point is always going to be at the center of the line, right? So if I move the endpoints, the point stays there relative. So what I want to do now is I want to do another one of these. I want to clone it, perhaps, but I would like to I would like this value, instead of being a relative distance along the line, I would like this value to be an actual Euclidean distance, so a distance in world coordinates. So if in the world coordinates this is 5 units, so I would like this to be like 1 unit, 2 units, 3 units, whatever that is. Okay. Because I want to plug that in to the video, just to give like more options or more alternatives for the video. Whew, yeah, this is not going to be easy today. All right. I have a headache, and by being slow and sloppy, I'm probably going to give you a headache as well. Sorry. I'm not sure what can I do about this. All right. Let's focus. Whew. So what am I going to do now? Yes, I'm going to start this clip by describing what we've done and then describing what I want to do. Yes. Okay. Before we finish this video, I want to implement like a slight alternative or like a slight version to this algorithm. And because I want you to keep in mind that what we've done with this algorithm is that we have calculated a point along the line, but the coordinates that we have used have been relative to the length of that line segment. So for example, here if we choose 0.5, we know that no matter how long the line, the point is always going to stay at half the distance. Oh, what am I doing here? Uh, all right, let me start over because I was extruding that point. Oh, what have I done? All right, starting over. Okay. Is my camera where it should be? So if I switch to this and this, yes, it's good. Okay. Before we finish this gem, I would like to show you like a small variation or a small alternative to this algorithm, because we need to keep in mind that what we've done here is we have calculated a point along a line, but we have used relative distance as the measure. So for example, if we have 0.5, this doesn't mean 0.5 units in the world coordinate. What it means is halfway through the length of the whole line segment. So if I move, for example, this point all the way up, or if I move it all the way here, you can see that the calculated point, always stays at the middle, at the center of the line. So that's great, and that's actually much more useful in many applications, in many situations, but we may want, for some reason, we may want to calculate the point along this line instead of in relative terms. We may actually want to calculate that point in world coordinates. So for example, if this segment here is 5 units, we may just want to calculate this at 5 units, 2 units away, 7 units away from the starting point, whichever units that might be. So that's actually very easy to do, and I would like to implement that version here real quick. So follow with me. Okay, so how are we going to do this? I'm going to copy and paste this thing. I'm going to add here another parameter. This one is going to be called D, and I'm going to change this, and it's going to go from what? From, I don't know, from 0 to 10, for example. I'm going to put it here in the group. Then I'm going to replace this with D, and I'm going to plug this in here. I'm going to turn this off, and then here, point along the line. We had a function. We did a function. We defined a point at a relative distance. Yeah, so I can probably just create a new function here and rename this point along line relative, and the other one being point along line absolute. And then how are we going to do this? So basically we're going to calculate the distance, the length of the line. We're going to use the distance to calculate the relative position, and then we're going to go back to point along line relative. And that's actually, I like that model because it's going to be one function calling the other, so it's kind of like implementing an overload, which is an interesting technique. So should I explain that with a sketch? Do I have the sketch? I should have the sketch, right? Do I have the sketch? Sketchbook, open recent. Oh, I do have the sketch. So should I explain this conceptually first, and then I could probably implement this first. Hey Leonardo, good morning. I should probably explain this conceptually first, and then I can just go here. Okay. All right. So let's do that. So where's my drawing? Okay, here. So I'm going to add. Where are we? Where's my mouse? I've lost my mouse. Ah, here. All right. So. Okay. All right. So here. And if I say, what do I say? What am I going to say? If I say that this is, okay. If I say this thing here, I'm going to use a different color. Can I use a non-RGB color? There used to be a color palette somewhere here. Image, color puck, yes. So can I, is this, yes. Ooh, and I like orange. Yeah. So if I say, if we're looking at this distance, and this distance I'm going to call it d, lowercase d. And if we're looking at this distance, and this is going to be, actually let me do that in a different layer. And let me save this, another layer. And if we say this is going to be uppercase D, the only thing that we need to do is we just need to say D, capital D, divided by big D equals n, the normalized length. And then there you go. And then with this we can plug into what we had already before, and you can see this from here. Okay. Hey Barbara, good morning. How are you doing? I guess you probably have a headache too, huh? All right. And then here. Okay, so we're good with that. So I can probably just turn on this and this and this and this and explain it this way. All right. Okay, so let's do this. Okay, so yes. The way we're going to do this is actually super simple, and it goes back to understanding how we did the previous algorithm before. And since we already know how to do it for a relative length, the whole idea here is that it's very easy to go from absolute distance to relative distance, because if we think that that this distance, the distance where we want the point to be, we have it in world coordinates, so in real units as opposed to relative. And if we think that the total line segment is however much long, so we have like the length of the line segment, and we also have the length at which we want our point to be, then it's just so simple as saying, well, if we divide the length at which we want the point divided by the total length of the line, then basically that gives us n, which is the relative length at which that point is along the line. And therefore now we can go back to the technique that we had before and find where that point is based on its relative length along the line. So by using this formula, the distance where we want the point divided by the total length of the line, that gives us how far along the line this point is, and then we can just go back to the previous. So let's just do that. Yeah, let's do that. All right, so let's do that. Okay, so I have this, and then I'm going back to this one here. Okay, and so this is going to be, for example, 5 units, or whatever unit, however many units. What is the length of this line right now? What is the length of this line? Is 9. Okay, so this point is good. Okay, so I'm going to need to change batteries. Yeah, if you stop hearing me, just please like make the chat explode, because I'm running out of batteries on my microphone. I may need to change that very soon. Okay, back here. All right, so back to the coding board. So what I've done here is I have copy pasted the previous component, that one that used relative length. I've copy pasted it, and I have changed the slider, and I've created a new slider that is that has a bit more range, from 0 to 10, I think. I have changed the name of the input. I've called it lowercase d, just to make sure that we understand the difference between normalized coordinates and Euclidean coordinates, or world units. And then inside of it, I have come here, and I haven't really changed the code. I've only changed here to be d, but this is basically what we had before. Okay. So one thing that I'm going to do now is I'm going to separate the two functions. One is going to be point along line relative, all right? And then so I'm going to change the name here and here. And I run this, everything was well, okay? And I'm going to keep this, because what I want now is to create a similar one, a similar function where I say point 3D. I'm going to zoom this here probably for everybody. I'm going to create another function here, and I'm going to call it point along line absolute. And this is going to take a point 3D object A, another point 3D object called B, and then a double value. This one I'm going to call it V, so that it's a bit clearer that it's different. But this doesn't have anything to do with the fact that the component has a D input. It's totally unrelated. Okay, and this and I'm going to copy paste this. This function returns at an absolute Euclidean distance d between points A and B. And how does this work? Well, it's very simple. The only thing that we need to do is we need to first calculate the length of the line. Then we need to calculate n, so how far along the point is. And then we just need to call this function to find that point. So how do we calculate the length of a line segment? Do we have a gem on that? Did we do a gem on that? Have we? I don't even know. I think we did, right? Oh, here, we're live. All right. Point-to-point distance. Yes, it's point-to-point distance. We did that already. Okay. So let me pull up. Where do I have that code? Where do I have that code? Yes, geometry, gem 4, distance between 2 points. All right, this is good. You see, this is what I want, actually. I want to build knowledge incrementally, so that we can build upon what we've done before. So where is the, okay, so let me just save this. Okay. and this goes up. So distance between 2 points. All right, this is great. Okay, and then we go here, and then we have it here. Okay, I'm going to say that on the stream. Yep. Yeah, here. So I was with my head like this, right? So I want to keep my head like this so that when we do the video editing, okay. So yes, we did. I just realized we had this gem. So this is exactly what I want to do and build gems on top of other gems so that we can build more complexity. So if you can go back to geometry gems number 4, and here we did calculate the distance between 2 points, which is the same as calculating the length of a line segment. So I have gone back to the files and I have copied the function. So here, this is the function that we developed in geometry gem, distance between 2 points, geometry gem number 4, and this takes 1 point, 2 point, and gives me the distance. So what I'm going to do here is I'm going to say double uppercase D is going to be distance between A and B. All right. Now I'm going to calculate n. N is going to be equal to the Euclidean distance that I have as an input in this function, divided by the total length of the line. Okay. Now, as I do that, I can now say, let's find the point 3D P, which is at that relative distance between these 2 points. So I can just copy this and say between A and B and at the relative distance n. And then that is the point that I return back with this function. So that's going to be return P. All right. And I want you to notice something very nice and very elegant that we have done here. We have a function called point along line relative, and we have one that is absolute. But the absolute one actually relies on the relative one. It just does some pre-processing of the data and then calls the relative one with the normalized coordinate that we have calculated. This is a very common practice, and I find this a very elegant and very nice way of writing code. So I'm going to copy this here, point along line absolute, and then if everything went well, we should see now that this point, if I go to 0.5, it's not at the center anymore. It's like at 0.5 units, world units along the line. If I can increase this, and if I move the point, you're going to see that it's not going to stay at the same relative distance. It's going to stay at the same amount of units along this line. All right? So we have changed now from relative distance along the line to absolute distance along the line in Euclidean coordinates. Okay, and I think that's everything I wanted to do for this video. So I'm just going to wrap it up and then do an introduction. And then we can go into Chaikin's algorithm. Woohoo! All right. I'm actually quite excited about that. How's the microphone doing? All right. So I'm going to finish this. Okay, so that was it for this gem. If you like what you saw, please remember to subscribe to the channel, to hit I like, and all those things that people do on YouTube, and stay tuned for more on the channel and on the live streams. Thank you very much. And now let's go back to recording an introduction. So I'm going to turn this on and off. And we have the line here. And what do I want to say? I want to say, hi, we're going to calculate this, and the 2 ways we're going to calculate this, and that should probably be fine. All right. What gem is this? Is it the... Which one is it? 5, 6? Which one is it going to be? It's going to be Geometry Gem 6. All right. Do I even need to say that? No, I'm not going to say that if it ever changes the number. It's going to be... I don't want to be... I don't want that hard-coded in the video. Okay. Hello, and welcome to another Geometry Gem, where what we're going to do today is we're going to calculate a point along a particular distance along this line. I didn't like that. Hi, and welcome to another Geometry Gem. In this one, what we're going to do is, given a line, or as we usually do, given 2 points, we're going to calculate a point along that line at a particular distance. We're going to do it 2 ways. We're going to do it based on a relative distance. So you can see here, I have a point, which now is going to be, if I say 0.5, the point is always going to be at the middle. If I say 1, it's always going to be at the end, etc. But I'm also going to implement it in a way that it's an Euclidean distance, so that this point is going to be measured along this line in world coordinates, or whatever units you're working with in Rhino. I'm going to be implementing this with Rhino and Grasshopper, which is an algorithmic modeling environment, but all the code that I'm going to be using is being written in C#, and I'm going to be using no libraries whatsoever. So you will see that if this is of interest for you, the code that can be written and can be changed to any other, very easily to any other platform. I'm starting over again. I didn't like that. And I don't like this slider. I want this slider to go from 0 to 1. Yes. And I want this to be 0.5. All right. Okay. All right, let's do this again. Hi, and welcome to another Geometry Gem. In this one, what we're going to do is we're going to find a point along a line, or a point in between 2 other points. We're going to do it in two different ways. One is going to be by using normalized coordinates or using relative coordinates. So for example, this point that you see here, no matter how much we move the line or what it is, it's always going to be at the center of the line. And if we do 0, it's going to be at the beginning, and if we do 1, it's always going to be at the end. Those are relative coordinates, but also we're going to implement like a slight variation of that, where the units are going to be, instead of relative to the length of the line, are going to be in Euclidean values, or basically in world units. So if this is 5 units, 3 units, so the point is always going to stay at that fixed length along that line. All right. I'm going to be using Rhino and Grasshopper, which is an algorithmic modeling environment, just for the sake of having easy visualization of this algorithm. But the code is going to be written in native C# without any libraries. So if you will see that what you will learn from this gem will be very easy to translate to any other of your favorite programming languages. All right. So let's get to this. All right, and we're done. Yoo-hoo! Let me save this, and let me close this. Wait. Let me actually internalize this data for the whenever we publish the file. There you go. And all right, and I want to make sure that that file doesn't get lost. Yes. Alrighty. Okay. So, where were we? Chaikin's algorithm. Hmm. Okay, so... Oh, excuse me. Um, Chaikin's algorithm. Any any comments, suggestions before we move on? I have a question on a line n0.5 will output the middle point, but how could you compute the middle point in a nerves curve? Well, that is a completely different story, completely different game. Nerves curves have a different formulation of how they work. They use polynomials, so it's a bit more complicated mathematically. I'm not going to get into that anytime very soon, but we may actually get to that at some point here. But yes, and Arasto, that's usually the way to go. So you can normalize the domain you can normalize the domain of the nerve curves and then just find a point at 0.5 in that domain. However, you have to be very careful because we need to remember that with nerves curves, the domain of the curve may not be homogeneous, so may not be distributed like with the same density along the curve. So a point at 0.5 may not mean that it's exactly at the center of that curve. All right. So Rhino has methods to do that for you using Rhino Common, but we're not going to get that into how that works anytime soon. Like there's so much more foundational stuff that I want to get into that is going to be a bit farther down the road. I feel like taking like a quick break before we get into Chaikin's algorithm. I'm going to make a pause, 1 minute, 2 minutes, water, bathroom break, whatever you need, okay? And then I'll see you back in a couple minutes. Don't go anywhere. Hmm? No, well, you can go to the restroom, but not much farther away, okay? See you in a bit. Okay, let me change the batteries in this thing um, before we get our hands dirty. I do not want that to happen while I'm talking. Whatever. And by you, we lost audio. I was changing the batteries in the microphone. But you should hear me now, right? All right. Oh, Ricardo, thank you. I really appreciate that. All right. So you can hear me all right. All right. Okay. All right. Let me. Okay. So Chaikin's algorithm. Woohoo! I hear a lot of you had a lot of fun this week trying to implement that. Actually, I want to pull this up So on the Discord channel, we have the coding challenge section. We made this just for the sake of this one. And for example, Jim Juan, he actually made a blog post where he described his approach to the algorithm and he described the code. I think this is actually really really cool, and you should check Jim Juan's blog. He's been doing this for quite some time already. He has a lot of these breakdowns of the algorithms that he's working on and snippets of code. I think it's really interesting. He also does these GIFs where he tweaks the values, whatever. If you're watching Jim, I'm just going to suggest you use white background for your GIFs because otherwise they're very difficult to see. But that's a very personal. I'm an old cranky person, so I like things in a particular way. But he also did this thing where I will get to this in a second. The Chaikin algorithm is usually the algorithm is based on the ratio of 1/4, the points you find in 1/4 along the line. But he also made that a possibility to be tweaked so that you can control the shape of the curve. I think that's a very nice addition. We're going to implement that today as well. And he also, I think he wrote somewhere, so he thought about doing a closed but curve, but he couldn't figure it out. He shared the files here. Kartik also came up with his own implementation. I'm not sure he shared the code, but yes, it's basically here. Um, then Arasto, where are you? You're here. Arasto, you're in the chat right now. He also made it in C Sharp, and he did this really nice visualization collage of this is so cool. I like this very much. Arasto, I'm totally going to ask you to let us post this on the and Monique, who's also on the chat somewhere. Hi, hello, say hello, Monique. She did 3 versions of this, and she actually implemented closing the polyline, which is really cool. Uh, so yeah, exactly. So I mean, I'm super happy. I'm super happy with this. So, and we should do more of this. We should do more challenges, where we say a challenge and then we give people the chance to um, spend some time trying things out. Um, so yes, so that's that's the work that was going on Discord. Remember, if you're welcome to join the. I'm going to post the link again. You're welcome to join the Discord and join the conversation anytime you want. We also have a live channel, because we discovered the other day that we cannot. Only I can post links, URLs on the chat here on YouTube, and we wanted to make that happen. Oh, and I can see that Nishant Nishant has posted his own. Would you mind posting that on the actual coding challenge? I think it's a bit easier for me to see. If you're there, Nishant, would you mind just reposting this as well on the coding challenge channel, so that we have everything there and we can take a look. Um, all right, and well, I guess now it's my turn to do it. Hey, Jim, I didn't know you were there. Nice to see you. Really good stuff. Please keep it up. Keep it up with the blog posts. They're super interesting. Really good job with that, okay? And my suggestion, white background, if you want to. It just looks better. And just make it bigger. I mean, it's like a tiny GIF. Just make a big ass GIF that we can see the curve change over. It's nice. Maybe we don't really need to see that many sliders. Just we want to see the curve, growing, and enjoy the curve, enjoy the curvature. All right. As you can tell, I've drunk a little bit of coffee to try to go over the headache, and it's not going well. I'm getting excited. Okay. So, how are we going to do this? I think first I would like to explain what I want to do is I want to explain what the algorithm is, how it works, um, and a little bit of the history of the algorithm. Do I want to get into that? Um, I'm not sure. All right. Since I will probably do that by the end of the recording, if anybody is watching this and if anybody can gather like a couple of links of the history of the algorithm, I think there's a paper, there's an old paper. If anybody can find, I have the old paper actually. I have the original paper, so I can talk about that. I can pull it up. But if you can send me on the live channel on Discord links to the history of the algorithm so that I can pull them up by the end of the live stream and make a recording and make them part of the recording, that would be great. And so I probably want to do like sketching and drawing how the algorithm works. And then I probably want to do an implementation of the algorithm. And then after that, I probably want to do some variations um, of the algorithm. Um, what do I want to do there? Um, whew. I'm blanking a little bit here. Um, this is a paper about the algorithm. Um, it's not really the algorithm. Yeah, but this is a diagram of how it works. It's actually um, pretty easy. Uh, bu- 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 Yes, so I probably want to. Uh, I probably just want to talk about the algorithm first, describe it. All right, and I'm just going to pull up the paper. Uh, this is the original paper. Is it the original paper? No. Yes, this is the original paper. Um, so I may want to start with this. Um, I may want to start with this. Talk about why it was important back in the times, and then describe um the algorithm with some sketching, and then just do coding. Um, that sounds like the easiest way to go about this. So I want to show this paper, then I want to show this other paper that has some diagrams. Uh-huh. And I want to show this because this is Paul. This is George Chaikin's son. And I met him recently, and that's actually the reason why I got the idea of like doing this on the channel. So I probably want to show that, and there are some a way of doing this in processing. And I'm going to show Jim's blog post also. It's really interesting. Um, so yeah. So I'm going to start with the paper. This other paper describes the algorithm. And then the demo here, and I'm going to show, yeah, that's what I'm going to show. All right. Okay, let's do this. Whew. Okay. Oh, I want to show this other paper too. Yeah, this is the one that proves that it's a piecewise quadratic curve. Anyway, yeah, I can show that. All right. Okay, let's start with a little bit of history. I'm a professor, so I like not just writing algorithms, but talking about the history of what those algorithms. So this algorithm is pretty interesting because it was invented by George Chaikin in 1974, and we have to think that in the 70s, computer science and especially computer graphics was still very much in its infancy, and computers had very limited resources to drawing things on a screen. So coming up with algorithms to design or to display things such as smooth curvature, um, as opposed to just polylines, was actually something that a lot of people were working in. And doing it in an optimized, fast way in a computer that didn't have many resources, that was something very important back in the times. Right now, in 2020, we give all those things for granted because our computers are just like 3D, blah, 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 whatever. But back in the time, it's like 50 years ago, um, it was actually quite a big deal. So this algorithm was very interesting because from something as simple as a controlled polygon, so for example, just 4 points, it was able to generate something that felt like a smooth curvature. It's not exactly a smooth curvature because at the end of the day, in computer graphics, everything, circles, curves, any Bezier curves, sine curves, whatever, at the end of the day, is just a discretization of that into small pixels. But if you do it fine enough, then for the human eye, it looks like a smooth curvature, right? So this is what the algorithm is about taking a sequence of points, so for example, these 4 points or more, and coming up with a way of discretizing that in smaller segments, so many that it feels like it's a smooth curvature, all right? For example, like the way we're seeing here for 1, 2, 3, 4, and 5 control points, okay? And the idea is that this algorithm was really simple and it came up with a very nice and elegant and fast way of doing this. And that's why it was very popular at the beginning in the 70s. And actually, there was another paper the year after, also published in the same journal, that proved that this algorithm was actually a way of creating a piecewise B-spline quadratic curve, which means that I'm not sure if I should get into that, but basically concatenating continuously a bunch of quadratic B-splines, which is what this algorithm, the result that it gives you. If you do some Googling, there are some papers out there that talk about the algorithm, and this one is, for example, is very helpful because it gives us a very nice description of how the algorithm works, and I'm going to explain this with a sketch in a second. But also, if you just do some Googling, there are a bunch of other, there are a bunch of like online places where you can see like how to write this algorithm, etc., etc. One of the most interesting ones is the one that Paul Chaikin, his son, the one that he wrote on his own website, right? And here you can choose to move the points around and you can choose like levels of discretization. So, and I will also explain why this is. You see, 0 iterations, it's a polygon. 1 iteration, it starts to be a curve, but it's not quite there yet. 2 iterations, it looks smoother. 3, 4, and at some point, there are so many iterations that it actually does look smooth. But remember, it's just like tiny, tiny line segments one after the other. I will explain this in a second. And I also want to highlight this link. This is by Jim Juan. He's one of our followers, part of the community here at Parametric Camp. For this video, I issued a challenge in my live stream, and participants in the live stream were given 1 or 2 weeks, I forget, to try the algorithm themselves. And Jim actually wrote a full blog post about writing the algorithm, his findings, and how he did that. On his website, and the hurdles and the problems that he found. He couldn't include the endpoints, and he still wasn't able to figure out the closed polyline situation. So this was really interesting, and I encourage you to check this out. And if you want to learn more or alternative ways of doing that, but I'm going to try my own way on this video, on this gem, okay? And what I'm going to do is, in order to start that, I'm actually going to explain how the algorithm works. So let's do some sketching on the whiteboard. All right, great. So, time to draw. I'm going to close. I'm going to keep this one. I'm going to close this one. Oh, I see some links coming up on the live. Thank you. In processing, Science Direct. Is this the paper on Chaikin's algorithm? Oh, okay. So somebody found, Arasto, you found, this is the second paper that I just showed on the video. This is the one that talks about Chaikin's algorithm, and that proves that the implementation is the same as producing a piecewise quadratic curve, quadratic B-spline. But this is not the original one. The original one is from 1974. But can you please find the link? It would be nice to have that link. I forget where I got it from. Well, is that true? Because I have OCD, so I usually just record those links. So this is that paper the link that you just posted, and this one is, yes. So if you look this up, it should be there. Oof. Sorry. Oh, oi. No, an algorithm for high-speed generation of curves. I forget what I got. This one. There you go. This is the link to the paper. I'm going to post it on the Discord. This is the link to the original paper. All right. Yep. Oh, this is us. Have you guys ever seen this? This is what I see from you. I see how many people are connected. I have some links, and then I see the conversation here. But I don't really know who's there. So that's why it's very useful for me if you guys say, hi, I'm here, blah, 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 etc., etc. Okay, so where were we? We were going to draw some sketching. Okay, so sketchbook. Okay, and we have this, so I'm going to save this, and I'm going to start a new one. We should do it the right way, right? The right way is taking a little bit of time. Chandra, you're asking for the full PDF. You can go to the Discord, and on the live channel, we have posted links to the papers, okay? So you can download them from there. Okay, so let's do some drawing. I'm going to draw, what am I going to draw? I'm going to draw a control polygon. I'm going to draw the points first. Let me draw some points. So let me draw, for example, oh, no. Let me draw a point here, another point here, a point here. Am I just drawing the same points on this diagram? Probably. A point here and another point here. Alright, and then I'm going to create a new layer and I'm going to do some light gray and I'm going to join this with, I'm going to create a control polygon. Oops. Okay. And how do I... Alright, nice! I'm getting so much better at this. And now I'm going to put this underneath. Okay. And then how am I going to do this? So the next thing that I do is we find the point at a quarter and 0.75. So some people can ask in Science Direct, we'll pay some dollars in each paper. Oh, okay. Yeah, I don't know what to do about that. I think I go through my library, and that's how I get the papers. But I'm not sure how to do that, and I'm not sure if I'm legally allowed to share those papers. If all right, we may have to find a way to do that. Okay, so what we do is now that we have this, now wait. We find yes, let's save this. And now we create a new layer, and the new layer is going to have new points, and that point is going to be one. No. One point is going to be here and here, and then here and here, and then a quarter and a quarter, a quarter and a quarter, and then we join those with a polyline. That polyline is going to be blue polyline, and then I'm going to create another layer. So that's going to be this one. Nope. Sorry. So this one, 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 and this one. Okay. And after that, we do the same thing again. We find this point at a fourth distance, at a fourth distance, at a fourth, blah blah blah, and at a fourth distance, and then after that we create a polyline, and this one I'm going to do it same color. No, sure, I'm going to do green, and then it's going to be this one, 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 here, 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 and here. Okay. And should I try a third one? That's gonna be crazy, right? Let me just do, yes, so why not? So third one is probably going to look something like this. This one, 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 here, 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 this is very difficult to do on a vertical screen. Yes. And wait. And then the final one is going to be red. Now, do I want to do it red? No, because then I won't be able to see the points. And then here, this. Okay. Okay. Boom. And then we turn everything off, and then it should look like smooth. Ah, oh, that looks nice. um, okay. Um, so, all right. And so what I would like to make sure is that we have this. Okay. Oh no. I threw everything on the same. Oh no, I don't like that. Ah, that's kind of bad. Yes. Okay, so let's redo this then. Because I want things on separate layers so that I can turn them on and off and explain the algorithm better. So I want this point, this point, this point, this point, this point, this point, and this point. And now I want another layer where I draw the curve, the polyline. And here, 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 and here. And this we can remove. So now we have, oh, okay. And so when we draw the points, okay, have a points, and then in these ones, so here I want to create another here, and I want to draw that this is 1/4, this is also 1/4, this is also 1/4, this is also a 1/4, this is also 1/4, okay. So now I can say we have a points, we have all the points, we draw it like a control polygon, we don't need that, and then we draw points at 4th, all right? And then we draw a curve between them, and then we subdivide this even more. We can turn this off now, and then, yeah. Okay, I think this should do. Okay. Okay. Yeah, I don't know what to do about that. And about access to the papers. It's part of like if I got the paper through my academic affiliation, I'm not sure if I can just reshare that openly. It's probably not part of the copyright agreement. I don't know what to do about that. Anyway, so we're going to save this. we're going to open. Okay. Okay. So let's explain the algorithm then. All right, so let's talk about the algorithm. And I actually love this algorithm because it's so easy and so straightforward to implement. Yet the result is so nice but you're gonna see like very soon. So let's start by imagining that we have a series of ordered points. So point number 1, 2, 3, 4, whatever, which we could use to draw a polyline along them. We don't really need the polyline for the reasons that I will explain, but it's all about thinking of those points and conceiving them as the control polygon that is going to drive this curve. The next step to the algorithm, this is an iterative algorithm. So what we do is we perform a smoothing operation on this control polygon many times. However many times depends on us. So the choice that we want of how smooth or how refined we want that curve. But the process is as follows. We go through iterations of smoothing this control polygon by doing the following. For each one of the segments, so for each one between 2 points, what we do is we find points. We find 2 points between any series of 2 control polygons. Not control polygons, 2 of those points in the control polygon, with the rule that those points must be at a fourth of the starting point and a fourth of the end point. So you can see this point here is at a quarter of the relative distance to this point, and this other point is a quarter of the relative distance to this other point. This one is a quarter into this line, this one is a quarter before the end of the line, this one is a quarter, etc., etc. So you see where I'm going with this, right? And then as you have subdivided those you have created new points for a new control polygon, so you can join those points with a polygon, and then you get the first iteration of a smoother polygon than the one you started with. If you do this iteratively, so now if we take this control polygon and then we do the same thing, we find in between every pair of points, we find these new control points, so at a quarter distance from the ends, and then we join them again, you can see that the result is like yet a smoother curve than the one we started with. And if I repeat that process again, for example, you can see that I find a lot of points at a quarter of the end points, and if I join those again, then you can see that I end up with a much smoother curvature here. So this, as I said, we did this just for 3 iterations, and the curve actually looks pretty smooth already. So if you go all the way up to, for example, 6 iterations, then it's very difficult for the human eye to just to distinguish like the tiniest length segments. But this is the core of what we're going to be doing, just basically finding for an original set of points, we're going to be finding for each pair of points, we're going to be finding 2 points in between them at a quarter of the relative length of the curve, and we're going to use those new points to create a new control polygon like this. And we're going to do that iteratively, over and over, a controlled amount of times. I think a good rule of thumb is about 6 times to create like nice smooth curvature. But this is the core of the algorithm. You can see it's very simple. The only thing that we will need is to know how to calculate a point at a relative length between 2 points, so a point at 0.25 and another point at 0.75 in between these 2 points, and to do that iteratively. And for this, for the calculation of the line of the points between 2 points, I already have a geometry gem that we did last week. I think it's number 6 or so, but you can look it up on the channel and it will pop up. Probably it will be on the link here in the description, or it will pop up somewhere as a card. All right. So it's just as simple as this. So how about we give it a try to implementing it? All right. Um, so I think that was good. So I think it's time to go back to Rhino and see how can we implement this technically. It should be pretty straightforward, I hope. I haven't prepared. I haven't done this before ahead of time, so it might be a little bumpy. So maybe what I do is like I just give it like a really quick try, and then I go back and record the well thoughtful video, um, the well thoughtful video. I'm gonna take a small break, 1 minute. I need to go get some water. I'll be right back. All right, I'm back. How are we doing? Was the explanation clear with the diagram? I mean, half of you have already implemented the algorithm as a challenge, so you're probably like, oh my god, this guy, come on, let's get to more fun stuff. Are you thinking of what could we do for a next challenge? Can we talk about that on the Discord? Um, so either on, okay, so either on the coding challenge, channel or on the live channel, more on the coding challenge. Is there something we can think about for a challenge that we can work on for next week? Um, I'm just gonna throw that out there. If you guys want to start thinking about that. Okay, so what are we doing here? I'm going to drop like a bunch of points here. For example, these ones. Should I do this on the video or should I just prepare this? I'm going to do it in the video for those who may not be very familiar with Grasshopper. Um, I'm going to do it in the video. Yes. Mm-hmm. Oh, I think I may have more microphone problems. If you stop hearing me, please let me know because I may need to change the batteries of the receiver, the microphone receiver. Okay. Okay, let's prepare our file. So what I'm going to do is I'm here in Rhino, and what I would like to do is I would like to put here like a bunch of points. So I'm clicking on point and I'm clicking left mouse to create a point and right mouse to repeat that action. All right. And I want to have the points here in Rhino because I will want to like drag them and move them to prove how nicely the curve that we create adapts to the control polygon. And now here I'm going to double click and I'm going to create a point container. And this point, I'm just going to right click and I'm going to set multiple points. I'm going to set this one, and remember that the order in which we set them is important. You can see that I can see the order because Rhino is already giving me this kind of control polygon. I'm going to drop some bifocals or bifocals, so that those who are not used to icons can still see the names of the components. And I'm just, for the sake of visualization, I'm just going to create a polyline between these points. This is just for visual flavor, but we don't really need that polyline at all. And to create a C# script component, I'm going to double click, create C#. I'm going to rename the inputs. For example, right click. I'm going to type here PTS, as in points. And here I'm going to, for example, iterations. So how many times do we want to iterate over this curve? And I'm going to right click on PTS. I'm going to make sure that this has list access, so that instead of reading one point at a time, I can read them as a list. So that's one thing. The other thing is that I want to make sure that the type is .3ds. Similarly, for iterations, I want to make sure that it's on item axis, so I just want one number, and that the type of the input is going to be of the type double, because I want numbers to be here. Actually, you know what? That's not right. I don't want doubles. I want integers, because I cannot do 1.3 iterations. So that has to be an integer. And then here, I'm just going to drop a slider connected to iterations, and so that I can control whether if it's 1, 2, 3, 4 iterations, whatever. And then right here inside, now I have my my C# scripting component ready, which at the end of the day is just this one function that Grasshopper gives us that contains a list of .3D objects, and this is a list because I clicked on list access, and an integer, which is the number of iterations, with the result being a referenced object, which I'm going to I'm going to say, for example, I'm going to call this I'm going to call these points out, for example. And if I double click here, you can see that the reference is now points out. All right. And given this, I am now ready to start writing some code and making this happen. I think the first thing that I'm going to do is I'm going to bring in the function that calculates a point at a relative distance between two other points. And we implemented that in a previous geometry gem, which you can probably find somewhere on the links. So let me go and find that and bring it back here. Okay, so where is that? I probably want point along line. Yes, so that's this one. And it's going to be this function here. And that is going to be, and yeah, so I can paste it here now. And that was, what is that going to be? It's going to be geometry gem. Which geometry gem is that going to be? So geometry gems is probably going to be number 6. We haven't published it yet, but it's going to be number 6. Okay. Right, so I went back through my videos and I went back to geometry gem number 6, in which we discussed how to find a point at a relative length. So I did copy the function that I created there, which is called point along line. A and B and T is the relative distance along that line. I'm going to just write here from geometry gem number 6, okay? Which, as I'm recording this video right now, still is not published, but it will be published very soon, okay? So if you wanted to know how this works, just make sure that you go to the geometry gem, all right? And now here, we are ready now to implement the algorithm to do recursively to find many of these points. So let's take a look at how would we do that. All right, and how would we do that? I have not given this any thought whatsoever. So, how is that going to work? I think probably what I want to do. Hey, my glasses. So, probably what I want to do is I want to write an algorithm that starts with a list of points. Starts with a list of points. And then from that list of points, calculates all the new points at 0.5 and 0.75, right? Substitutes those, and then does that over and over again. Is this something that I want to explain with a diagram, verbally? I may want to explain this with a quick diagram. It doesn't really hurt, right? Yeah, why not? Let's just do it on a diagram. I mean, visual thinking is always helpful, right? So why not? Yes, and we probably want to do we probably want to use a function called smoothing or something like that. I think that's how Jim did it, which is probably quite helpful as to keep things. Yes, so yeah, I think you probably want to do this. Where is my mouse again? Oh no, where did you go? Ooh. Okay, new layer. Maybe this layer goes here. Okay. All right. So what I'm going to do is I'm just going to explain this as I'm just going to draw it as I explain it. Okay. So the process for the computational algorithm is going to be also super simple. Let's imagine we have a list of points, okay? A list of points that is going to be, these are going to be the control points. What we're going to do is we're going to create some kind of function or operation that we're going to call smoothing, for example. So we're going to smooth these points, and as a result, what we're going to get is another list of points, which are going to be all these points here in the middle. This one, this one, this one, this one. So we started with the original control points, so these ones, and as a result of smoothing, we end up with this list here, which is this point, this point, this point, all of these points here, right? And again, remember that we don't really care about polylines. What we care is about an ordered list of points, which is the same thing as a polyline at the end of the day. And then once we have this, we can just repeat this process as many times as we want. So we can just take these points and make them those original starting points that we then smooth again, over and over again. And how many times we do this, this is going to be defined by our iterations. And I don't know how to write that. That was a terrible diagram. So we're just going to have a list of points that we're going to keep mutating and subdividing and smoothing according to this particular rule that we have devised. Okay, so let's see how that would work code-wise. All right, so something that I want to check out before we start is how to clone a list in C#, how to copy, how to, you see, and it's not the first time that I've looked it up. I think you can feed the list. Okay. Is there an easier, you can use an extension? I don't like extension methods. I think, yeah, this is what I want to do. This is a better response. You want to deep copy, but we're not, because it's just structures. It's fine. Okay, we don't need that. Yeah. So, okay, so let's start by doing one iteration of this process, and then we implement how a full set of iterations would work. So let's start by creating that list that we're going to be working over and over again. So create our working list of points, and I'm going to call that, for example, that's going to be a list of point3D objects that I'm going to call control points, for example, and that's going to be a new list of points, which I'm going to control points is like a new list of points 3D objects, and something that is usually good practice is, instead of working directly with the input of the function, working with a copy of the list that is coming from the function. In Grasshopper, that doesn't really matter much, because at the end of the day, everything is copies. But if you're working in a different environment, you probably don't want to mess with the original list that you got. So it's probably usually good practice to copy as a clone or as a copy. And we can do that by creating the new list of point3D objects, and here in parentheses, passing in a list that we want to copy. And because these objects are structs, they're not classes, we're probably going to end up with a copy of this list. Okay? Then what we may want to do, and this is just one iteration, what we may want to do is something like saying, I'm going to create another list that I'm going to call smooth points, and this is going to be the result of some kind of smoothing operation. So for example, smooth polyline, which I haven't implemented yet. I'm just like designing the algorithm, and this is going to take as an input these control points, and it's also going to take as an input the smoothing value. We discussed how this is a quarter, right? And then after that, we say the output is going to be points out, for example, which is going to be these smoothed points. Not pots, but points. All right, and obviously if I run this, it's not going to work because there's no smooth polyline function at all. So the name smooth polyline doesn't exist. So I'm going to go here all the way down to custom additional code. This is where in C# script components, this is where you add your functions. So this is the global scope of sorts. And here I'm going to create that function. And the input, as we said, is going to be a list of point3D objects that I'm going to call points, for example. The fact that this is called PTS has nothing to do with this. It's independent. And then a double value, which is going to be, for example, T. And that is going to be where, along those lines, those control points are going to be found. All right? And then we need to remember that we also have to implement here the return type of this function, which is going to be another list of points. So it's given a list of points and it returns another list of points. So it takes, going back to the diagram, it takes the original control points, all right? And then it returns a new list of control points, which are the ones in the middle, these ones here. Oh, so much stuff. So Now I'm going to add some code here. Returns a list of smoothed. Is smoothed a good English word? I'm not. I don't know. Of smooth control points for the polyline. All right. And then here is going to be very easy. What we're going to do is we're going to create a for loop where we're going to go over each pair of points, this one, this one, this one, and we're going to find the two control points that we need in between those two lines, in between those 2 points, and we're going to add them to a list, an empty list that we're going to keep populating with these points. So how does that work? Let me create a list of points, 3D objects. For example, new points. And this is going to be a new empty list that we're going to initialize here. Empty list to populate with new points. And now we're going to write a for loop to go over all the original control points. So this one, this one, this one, this one, this one. So this for loop, I'm not going to start it at 0. I'm going to start at 1, so that for each point, for this one, for this one, for this one, what I do is I look at that point and the previous one, and then I calculate the points in between. So I'm going to say for a for loop that starts at 1, and that is where I is less than the length of points, and I increases 1 by 1. All right. What I'm going to do is for each pair, I'm going to take for each pair, I'm going to say the first point is going to be point A, and the second one is going to be point B. When I do the second segment, this is going to be A, and this is going to be B. For the third segment, this is going to be A, and this is going to be B. How is that? I'm going to create a point 3D object called A, and that's going to be, in points, is going to be the point that is at location I minus 1. All right, and point 3D B is going to be, from the points, is going to be the one that is at location I. Because remember, I started counting the for loop. If this is point 0, I started with point 1, point 2, point 3, and point 4. So I want to take that point and the previous one. So that is point A and point B. All right. So as I do that, I can say let me calculate the point D. I'm going to call that, what am I going to call that? B0 is going to be a point along this line between A and B, which lies at 0.25, right? And then point 3D, P1, is going to be a point that lies along that line at 0.75. As we have those points already, now to the list that I have created, I can add P0, and to the new points list, I can add P1, and this for loop will take care of going through all those points and calculating the 2 points in between each pair of points. So as we finish this for loop, this list here should already have 2 points per segment of the polyline. So now I can just return new points, and this should work. So is that going to work? Let me say, oh, no errors. And what if I plug a panel here? I have a list of points, and you can also see that these points here, I have a collection of points that are at 25, 75, 25, 75, etc., etc., along each one of these. And if I move the polylines, you can see that things adapt nice and smooth. All right, and very importantly, for these control points, I do not have this point, this point, this point. Those are not in this bucket here. So this is working well, and I have been able to do one iteration of this, but I skipped through some things, so the code is not very tight, and also we don't have like a full iteration. So let's do a couple fixes there. You might have noticed that here I just hard-coded 0.25 and 0.75. But this is not great design because the input of the function allowed me to customize that parameter. Here I'm calling it with 0.25, but I want these two values to be linked to that length, that relative length that I want to calculate. So how can I do that? Very easy. So I can just compute the relative lengths of the points. So that's going to be, for example, I'm going to call the first one t0, and that's going to be equal to t. And so just that value. And then t1 is going to be equal to 1 minus t. So if this is 0.25, 1 minus 0.25 is 0.75. So now I can substitute here t0, and I can substitute here t1. This is going to give me the same result. But what's nice about this is that now this allows me to play a little bit with that parameter as an input. So for example, here I can say, for example, t, or not, I'm using this too much. I'm going to call this proportion, for example. That's a terrible name. But if I write a slider here and I plug it in here, I make sure that this is of the type double, and then I replace this hard-coded number. I really don't like hard-coded numbers in algorithms. So, and we replace this with prop, okay? Now I got the same result, everything is working well, but you can see that I can now customize where those points are along my line, and I can even flip them, you know? Whether if this will be interesting or not for the curve, I don't know, but this is the kind of things that I like doing when I'm doing computational design. I like to challenge values and I like to challenge numbers and see where I get with them. Let's keep in mind though that the original algorithm says that this has to be a quarter of the length of the line. This has to be 0.25 to be the original Chaikin's algorithm. And it has to be like that in order to generate quadratic B-splines between the control points. Otherwise, it's not the original algorithm, it's our own interpretation of the algorithm. This is very important to notice, okay? All right, so I think at this point, we are ready to now change the code a little bit and implement iterations of this. Let's take a look at that. Oh, I should have plugged in here a polyline to better show this. Yeah. Yeah, all right. I can do that right now. All right, how is this going? Is it clear? Am I too slow? You guys can call me out if you think I'm being too slow on this one. I just like making things clear and solid. If you already know me already. Is anybody there still? Okay. So yeah. So, all right. Thank you. So let's take a look at how to implement that recursively. And what we're just going to do is we're just going to substitute this with we're just going to wrap this inside of a for loop, and we're going to override the control points. Oh yeah, I still see people. Thank you. Thanks for saying hi. All right. Okay, so let's go back to the diagram. Right, so going back to the diagram that we showed before, what we're going to do now is just in order to perform several iterations of this process, what we're going to do is we're going to take the original list that contains the points, we're going to smooth it, but then we're going to overwrite that list over and over again, how many times, however many iterations we want to implement out of this. So that's going to be super simple. I'm just going to go here. Oh, and I forgot before, something very cool that we can do is we can just join all these points with a polyline so that we can see how the polyline is actually smoothing, right? So I'm going to double click here, and you can see that just to get things out fast, what I did here was I created a new list, all right? But something that I could have done is I could have just taken the same list and overwrite it with the result of the smooth polyline, and that make it the output, all right? Because remember, when you write code, very often, like 90% of the languages that I know of probably, statements are executed from right to left. So this gets executed first with whichever value for the points was coming here, and the result of that then gets assigned here, so it gets overwritten. So we can do this one time, or we can just wrap this in a for loop where we say, I'm going to create a for loop that starts at 0, where I is less than the number of iterations that we want to compute, and I++, and then we don't really need that I for anything. This is just a matter of controlling how many iterations we execute. So iterations of smoothing. And then once the result is done, then we just output that result. Let's see, are you guys excited? Is this going to work? Boom! Oh my god, we got something here. So we had 2 iterations, and you can see how the curve smooths from 1 iteration, 0 iteration, so that's the original, 1, 2, 3, 4, 5, 6, 7, 8. And you can see, if I turn off the control points, you can see that this curve, to me, this polyline, to me, looks like a smooth curve. My eye cannot really distinguish the tiny segments that are making this polyline at all. What is the limit? You see, I cannot see the difference between 8 iterations, 6, 7, 6, 5, 4. I can see now some, yeah. So 4, I don't like 4. 5 is already pretty smooth, but I think 6 is so many points that I can barely tell them apart. And so, yep. So this is basically Chaikin's algorithm. And something that is very nice about this algorithm is that it works in 3D as well. So the points that we chose were all on the plane. But if I move this point up in space, you can see that the logic of the algorithm still stands, and that the curve still works in 3-dimensional space. So this is also something very nice. It's very effective, and as you have seen, the code is like very, very simple to implement. It's very nice and very elegant. What else do I want to say? I wanted to say something and I forgot about it. What is it that I wanted to say? What did I want to say? I'm going to remember later, and I'm going to hate it. What did I want to say? Well, I want to play with the parameters, that's for sure. Okay. Let's take a little bit of time also to indulge in what we've done. I'm going to go back to 2D, and let's explore the idea of where those points lay on the control point. Because remember, the original algorithm says that the control points must be a quarter of the ends, But if we play with this, so if we make this value smaller, you can see that we have this effect where the curve is actually snapping closer to the original control points, the original control polygon, and it's doing some weird curvature here that is not very nice. But if I smooth it out a lot, for example, if I bring it closer to 0.35, 40, we also see that, yeah, it's more detached, but we also see these kind of kinks. So it's also, that's not very great. And if we push it farther, what is this? This is so cool. This is not a smooth curvature at all, but if we flip the points and we move them past, so the point that was here now is first and then the second, we create this sort of like fractal curve or of some kind. It's kind of like an inverted like Chaikin's algorithm curve. This is really, really cool. What is happening there? What? What is this? This is really interesting. Huh. Okay, I like this. And if we take it all the way to 1, we end up with this strange triangulation. Huh. That's very cool. From control polygon to smooth to fractal to triangles. Huh. This is very nice. All right, so long story short, or bottom line, algorithms are nice to follow by the rule, but keep in mind that I like being a designer, so I like challenging rules, and a rule that is driven by one number is definitely something that I would like to explore. What happens if I change that number? I'm getting a suggestion on the chat to give it 0.75. That's a really nice result as well. What if let me bring this back to 3D and see how those curves change, that geometry changes spatially. Huh, nice. It kind of feels like it sticks to the plane. And what if I give it 1? I get that, I get this like really interesting triangulation, huh? I wonder if this could be something that we could use to go from a polyline to a mesh with triangles. This could be an interesting thing to explore. Cool. All right, so going back to 0.5. All right, so this is the original algorithm, and I'm going to bring this planar. And I probably want to spend some time trying to implement also whether if this curve is going to be closed on itself or it's just going to be open. Whether if we want to make this curve periodic or not. So how about we give that a try? All right. How are you liking this? This is really cool. So, periodic. I have no idea how to do that. I think Monique was the one who figured it out, right? If you want to share on the chat or on the Discord some tips about how to do that, but I'm assuming it's just a matter of to the original list of points, just duplicating this one and duplicating this one, right? That's my intuition. So adding the 2 additional points at the end. Oh, Arasto, you also did it. Like, so how did you figure that out? It's just like taking the list of points here when you create this list here, and then just adding at the end of this list, adding the first point and the second point again, right? Just the last point? Only with one works? And do you still get the whole thing closed? Let me see. So let me add, I'm just going to try it out here before we make the video. And this is going to be a Boolean value. Did it work just repeating 1 point? Huh, okay. That is interesting. If periodic, then take control points and add control points 0, right? What is going on? Periodic item boolean and then a toggle. Yeah, I don't think it works with, yeah. No, just one point doesn't work. You need to at least add at least 2, I would say. Yeah, yeah, you just need to add 2 points to close the, yeah. So you need to add the first point and the second point. All right. All right, so how are we going to do that? Should I draw a diagram of that? Should I explain that with some kind of, yeah, let's do it the right way, which is, yes, so let's do it the right way. This is going to be fast. So, because I'm getting better at this, and this. So I'm going to up control and then what I'm going to do is, nope, I don't want to close that. I want to just save that here, yes, and then I'm going to create another layer where I'm saying this is point 0, nope, this is point 0, 1, 2, 3. And then another layer, and I'm going to end up somewhere doing something like this. This is going to be the curve. So what we want to do is we just want to duplicate. If we add another point here, so this is going to become number 4 as well, then we end up getting a new line like this. What just happened there? Okay, there, and then we end up extending this. Oops, nope. Extended this like this, so it's not enough, so that's why we need a second point, which we just say, okay, so that's going to be a 5th point here, and then for that, all right, okay. Yeah, I think that's going to work. Okay. Okay. So let's talk about this. The notion of how to make this curve that we're going to generate closed, or how to make it periodic, which is the technical term usually referred to for closed curves, is actually going to be very easy. So if imagine like a simple control polygon like the one we have 4 points and we have this polyline that goes around them. If we draw that curve, the curve that our algorithm will generate will be something like this. And remember that it doesn't really reach the first point or the last point, because we start taking like a fourth and a fourth and a fourth away, you know. So, but if you think about these points being the 4 points that we created and being 0, 1, 2, and 3, if what we want is to make this curve continue and start closing into itself, then a very simple technique to do that is just to work with a list where we extend the control polygon to loop over into itself. And to do that, it's just as easy as adding to the same list, duplicating this point on top of itself at the end of the line, so that if we created a polyline, the polyline would look something like this. So it would have like the last segment would be coming all the way here, right? So that feels like that should work, but it's not going to work entirely, because if you remember the algorithm will probably end up doing something like this. It will extend beyond the last point into this segment, but it will also stop here, because remember, we take like the end, we take like a fourth of the end of the extremes away. So what we need to do for this particular algorithms is we actually need to duplicate this point again all the way at the end of the list, making it the 6th point, or the one with index number 5, so that our polyline is something like this. It's 1, 2, 3, 4, and 5 segments, and so that the curve ends up wrapping on top of itself and ending up very nicely here at the beginning of the point of the curve. So that is very, very simple to implement. So what I'm going to do here, I'm going to add a new input. I'm going to call this periodic. I'm going to make sure that this is of the type Boolean, and then I'm just going to drop here a Boolean toggle. Okay, the Boolean toggle that I'm going to set to true, and then I'm going to place here so that I can control if I want this closed or not. I'm going to double click here, and here in the operations, when we create our list of points, the list of points is just 1, 2, 3, 4, 5, and 6. But if we want to close, or we want to make this curve periodic, what we can do is we can say, let's check if the user is setting it periodic, if the input, there's an input called periodic. So if this is true, or a shorthand for this is just to say if periodic, so that works exactly the same. I'm going to write here duplicate points for a periodic curve. All right, and if that's true, the only thing that I need to do is to my list of points, after the last point, I need to add a copy of the first point. So what I can do is I can say for control points, let me add at the end of that list a copy of the first point that is currently on that list. If I do that, you're going to see how immediately as I press play, the curve starts wrapping on top of itself, because there is now this one line segment here going here. But as I explained before, it's not going to close up nicely with this one, because we actually need to duplicate also the first point. So the second point on the original list. So when I do this and I press play, now you can see that it goes all the way and it wraps up very nicely all the way here. And obviously I can modify these points and I can move them around in 3D space, and the curve adapts very smoothly to the whole operation. And I think that's it. So again, we can play with the triangulation with the parameters. We can play with whether if it's periodic or not periodic. But this is a very, very simple polyline smoothing algorithm that comes from a very simple rule. And as I said, one of the nice things about this is that each one, so this by definition is a piecewise quadratic B-spline, which means that the curve that is going from this point to the center of this point is a quadratic B-spline. The curve that is going from this one to this one is also a quadratic B-spline, from this one to this one, etc., etc. And also, if I close them up, this segment and this segment. And I think that's it for me today. I hope you enjoyed the video. I hope you learned something. I hope you had fun playing with the parameters. And if you like what you saw, it would be nice if you like the video, if you subscribe, turn on notifications, and all those things YouTubers do these days. Thank you very much, and see you in the next gem. Woohoo! All right. Oh, introduction. You see, I was going to forget. Mm, mm. Okay. Um, all right. So, okay. So, how am I going to do this? I'm going to show the intro. Let me close this up. Let me make this. I'm going to keep the polyline here. I'm going to keep this here as well. And I'm just going to explain that this is a smoothing. So all these iterations. And then I can also close it or not. All right. So I think that should be cool. Okay. Intro. Ooh. Okay. Hi, and welcome to this geometry gem where what I'm going to show you today is how to take a polyline and implement a smoothing algorithm that is going to create a nice interpolated curve along. No, it's not an interpolated curve really. It's a B-spline. Okay, starting over. Hi, and welcome to this new geometry gem where what I'm going to show you today is how to take a polyline and write a smoothing algorithm that is going to create a smooth curve that is going to be touching this polyline over several iterations. So for example, if I have iteration 0, it's just the polyline. First iteration is like a it's not very refined polyline, but as I keep increasing my iterations, you can see how the smoothing definition is much nicer, and now it's basically a smooth curve. I'm going to show you how to make this curve closed, and I'm also going to show you an alternative to working a little bit with how these polyline smooths and snaps to the original contour polygon. This works in three-dimensional space, and it's a really easy algorithm to implement. And nicely, it also happens that every one of these segments between every one of these curves between the control points corresponds to a quadratic B-spline, if you're interested in why that's important and what that means. So I'm going to be implementing this in Rhino and Grasshopper, which is an algorithmic modeling environment, but I'm going to be writing all the code in C#, and I'm going to be using no libraries or no geometry kernels. So if you're interested in this, you will see how learning from this example will make it very easy to translate this algorithm into any other programming language that you may be working with. I'm just using this here for the sake of visualization. It gives me a very nice interface to see this geometry. Okay, so I'm going to talk a little bit about the history of the algorithm and how I was inspired to do this gem, because I actually met the son of the creator of this algorithm very recently. And I'll talk a little bit about the history, and then I will explain how the algorithm works, and I will show an implementation of it. So buckle up, because it's going to be a lot of fun and super interesting. All right, and I'm done. All right. Arasto, what is going on? Oh, did we not get this right? Uh, is the last point not cool? Okay, so let's write this. Uh, uh, so if we have one iteration, so I check the final periodic polyline and the end point and the starting point do not match but are duplicate points. Oh, I see. This one. Ah, I see. This one and this one, this one and this one. You are right. That doesn't look good. This one, this one. Yeah, that doesn't look good. Okay, what have we done? Ooh, are we spreading false algorithms over the internet? Is that what we're doing? Sorry, is that what I'm doing? Sorry. Okay. What if we have more iterations? Do we still have that problem? Is it just 2 points? It's just 2 points. It's just the 2 points. So there's an overlap of one segment, right? We could just remove the last point of the list. I know, but that doesn't feel clean, right? Why is this happening? I don't know why that's happening. I'm gonna take a look at that, and I may just add a comment, or like I may just like perform that, make that here, but I don't think I'm going to add that to the video because it's already super late, and it might be a little too much for the video. We can implement that in the comments. But it's true, it's not very clean. So let's just do that. Iterations of smoothing, remove the last point, duplicate point. So from control points, remove at control points dot count -1. And if we do that, then we just have that 1 point, and we still have a nice polyline closed. And is this working for any amount of iterations? So 1109, 1101, 1109. Yep. That is strange. I don't know why that's happening. But Arasto, you're right. Thanks for catching that, actually. You know what? Let me just say that on the video. Why not? Why not say that on the video? If we want to do things right, we want to do them right. And we gotta hold ourselves to good standards. That's what I teach my students, so why not apply that to myself too, right? It only makes sense. So let me just save this file. Chaikin. All right. All right. Okay, so let's just write like let's just record a small thing piece. All right, so let's do that. Okay, one thing that came up, and while we were recording this video, and Arasto on the chat helped me find this bug, is the fact that the algorithm is actually the output points. There are there is one point that is duplicate and is creating like one segment of the polyline at the very end, overlapping the first segment. So if you see here, the first point and the second point are duplicate on the list, which means there is one segment of the polyline that is overlapping on top of itself. And this happens no matter how many iterations you create. There's always the first 2 points are duplicate at the end, which it doesn't really affect the visual result, but we know that here there's this segment of the polyline is duplicate, and it's not a clean solution. All right, it's not a clean algorithm, and we like clean algorithms. We're very rigorous and parametric people, so why not fix that? So I'm not really sure why that's happening, but a really quick fix is just to remove the very last point of the list before outputting the polyline. So that's very easy to do. We can just go here and say, let's remove the last duplicate point from the list of points. After doing all the iterations, just remove the one that is at the very end of that list. And if we do that, you can see that now we do have the first point is duplicate, and that's what we want because we want the polyline to end on the first point, but we don't have that additional point creating the one segment overlap on the polyline. So the algorithm is a bit cleaner now, and thanks a lot, Arasto, for catching that, okay? All right, and I think, oh, only if the periodic is true though. Okay, so, all right. There you go. Okay, so this is how it's going to go down into posterity. So that will be the file that I will post on the thing. So I think with this, I'm done for what I wanted to do today. So I think I wanna do like a quick Q&A and questions. So I'm going to take a bathroom break, but if you want to chat or you have any questions, please think about them and put them on the chat. I'll be right back, just 1 minute. Right, and we want to be clean people, so I'm not happy with the periodic thing. So let me just go back real quick and just say, okay. And now let me just remove this, yeah, and write it as. Oh yeah, and a quick thing. This only happens if the curve is periodic. So if periodic, then that's when we remove the last point. Not in every case. Okay? All right. And I will add that to the video. Okay, so we're done. Any questions? Anything you want to talk about? There was a question before on the chat. So, Salvador, I have a question. Iterations are related with recursion. I'm a little confused by the term. No, they're not the same. Iteration is when you do an operation multiple times. So, well, actually, they are kind of related in a way. So, iteration is when you perform an operation like multiple times. So, iteration in this case, in the case of what we've seen today, this is iteration, for example, here because we are taking all the points of the polyline and we're iterating over each pair, right? So that's iteration. Now, but in general, as a concept, it's just doing an operation multiple times. Recursion, though, is when you perform an operation and you perform that operation on top of itself. How can I explain that better? Recursion is, I mean, we could probably Google like the technical term, but I don't want to do that. I want to explain it with my own words. Iteration is when you, recursion is when you perform an operation recursively. When you perform an operation many times on top of the result of the previous operation. How does that feel? It feels so that it's getting some of the point. It feels a little bit complete though. Let me do an example. The example here would be if you have a polyline, if you have a line, and you create a recursive algorithm that subdivides that line in half. The recursion means you take the one line, you divide it in half, and then recursively you take the result and you divide each one of those two lines in half, and recursively you do it again, so you have 4 segments that you divide in half, so now you have 8, and so you start doing that recursively over and over again. So recursion is iteration because it's a process that you do multiple times. It's just that the additional layer, the meaning of recursion, means that you're performing operations on top of the result of the previous computation. Imagine like going down a tree of operations, sort of. And in computer science terms, recursion is very often associated to the idea of using a function, but then using a function that performs an operation, and calling from within that function, calling itself multiple times. So imagine if we had implemented a way of smoothing the polyline where inside of this function, inside of smoothing polyline, we were calling smooth polyline. We were calling the function smooth polyline again. I believe and then we call it like, I don't know how, 5-6 times, and then when the result is over, we start backtracking the results, and then that's when we output the result. I believe I did a recursive algorithm when we did the polyline simplification. Let me pull that up. Where was that? Clean duplicates. No. The Umbraco. Raymer the Raymer, Douglas, Pecker. I think, did I do recursion with that one? Oh, this is not mine. This is a contribution. This one, is this mine? Oh, that looks terrible. Simplify polyline. Yes, so can you see how here within simplify polyline I'm calling the simplify polyline function? So in computer science terms, the concept of recursion is very often associated to this technique. From within a function, calling the function itself and going down a tree of cycles until you reach some limit. So you don't call the function anymore because like you have reached the maximum distance or whatever. And then you start returning back up on that bubble of on that cycle of recursion. You start broadcasting the results all the way up back the tree so that you end up with a result that has been computed recursively. I feel I did a terrible job explaining that. How do you feel, Salvador? Do you feel complete? Do you feel I explained that in a decent way? Uh, all right, Arasto, what is the next challenge? I don't know. I haven't thought of it. I should start thinking about challenges before time ahead, right? The whole Chaikin algorithm just came up because I met Paul Chaikin and because I didn't have time to implement it myself. But I think we should do that more often. So let me. I don't really plan ahead the live streams too much because this summer I'm very busy and I'm doing a lot of things, so I don't have time to plan things ahead. But I'm going to try to start doing that more often so that I can share a challenge ahead of time. Maybe I think about something this weekend and I just post it on the Discord, and then you guys can pick it up and do it for next weekend. I don't know what it's going to be. You saw my lecture on meshes, and you said something about creating meshes from point clouds. I was wondering if you could give some hints on how to write the algorithm. Well, that's not straightforward. It's very involved, and I don't think we're there yet. I would like to build more foundational stuff before we get there, and we write such a complicated algorithm. But long story short, you can probably do that in Grasshopper if you just take the point cloud and you do a Delaunay triangulation. It may not give you a nice result because Delaunay is not exactly meant to do that, but it will give you like a very decent result. Also, typically, point clouds that are coming from 3D scans and stuff, the software that runs those scans and those point clouds does a pretty decent job in giving you a mesh that already joins them. If you don't have that, then you have to do it yourself, obviously. But usually from the scanning software, you can already get those meshes. But yeah, we're not going to do that. I'm not going to do that anytime soon yet. You can probably get away in Grasshopper just doing a Delaunay triangulation with a point cloud. And do we need to use spheres instead of circles in 3D for it? No, it's much more complicated than that. So yeah, I'm not ready to go there yet. No, but I will in the future. What about the geodesic curve on a surface or on a mesh? That is also pretty involved, Andres. I don't think we're there yet. I'm not there yet myself, but you can do that in plain Grasshopper. So Grasshopper gives you geodesic curves on top of surfaces with components. The math behind that is pretty daunting, and I'm not sure in the case of meshes if the concept of a geodesic curve actually makes full sense. It should be an interpretation of the concept, but it's something that we could talk about in the future. Is there a blog with cool parametric algorithms you like? Well, who was this? Somebody on the Discord pointed out to a blog with like a ton of geometry gems. They're not blogs; they're just the code. I think it was Jim. Was it you, Jim? Jim Juan. Where is Jim? Are you there, Jim? Where do I have? I took a where? Oh yes, this one. This one had a lot of interesting and small like self-contained small gems that I found very interesting, like simple triangulation operations and blah. So those are a lot of really good candidates to do here. Um, so given 3 points, how do you find like the barycenter, the circle that circumscribes those points? I said all those like really interesting algorithms. So check it out. Most of them are not. Most of them are just the algorithms and with an exploration, with an explanation. But for example, here there is one that is how to find. I just ran into this one. How to find the middle point of a line, and that algorithm is basically like a subset of the more general gem that we did the other day, which is finding a point along a line. If the value that you find is 0.5, then it's a midpoint. And the only thing is that they're written in Java, no, in C++. No, they have C# implementations too. Yeah, so yeah, a lot of those are really good training material if you want to get stronger on writing simple geometry algorithms. Roberto, I had the same problem with Delne because of triangulation at the edge. I found this in the old Grasshopper page that worked a lot for meshing my scans. And I'm assuming you probably tried to paste a link, but it didn't work because I cannot see any link. We have a problem, Roberto. The YouTube chat doesn't allow people who are not moderators. It doesn't allow people to paste URLs or links. So if you can paste it on the Discord, on the live channel, which I'm looking at right now, if you can paste it there, then I can paste it on the chat for the conversation. Otherwise, I don't think you can do that yourself, Roberto. Are you on the Discord? So can you do it now so that I just posted right here? Just look for ball pivot on the Grasshopper page. Grasshopper 3D ball pivot. What is this? Finally got a run. Okay. Is this what you're talking about? Is this the algorithm? Topic suggestions? Yes, I think we got to the same yeah. All right, so we can take a look at that. But this algorithm uses an R tree structure, which we don't know how to use. So for me, it would be much more interesting to perhaps first describe that structure, how it would work, and make an implementation of our own, and then go into the ball pivot algorithm. But yeah, that's actually a pretty good suggestion. Thank you, Roberto. And are there any other questions? By the way, Arasto, thank you very much again for picking up that bug. It was very nice to be able to fix that while and on the recording. All right. So all right. So I think that's it for me today. Thank you, Roberto. I appreciate those words very much. Okay. All right. So I think with this, I'm ready to start the weekend. I don't know about you, folks, but I'm gonna go out and enjoy the sun because it's very nice and sunny out here today. I'm not losing my summer, don't worry. And I very much enjoy doing this a lot. So if I have to go away for the weekend and hike, it's okay. But I also enjoy spending the morning nerding out and writing algorithms with everybody on that. So it's my joy. It's not a loss of any kind. Well, thank you very much, everyone. And see you next week. Next week, I have a wedding in the evening. but I think I will have time to stream in the morning. So yeah, so see you, everybody. Have a good one. Bye bye. Thank you.